Okay, this is my second attempt at 5C. The first one I hit the stop button accidentally and it actually stopped about halfway through, so we're going to start it again. And what I want to do first is talk about the August 2006 decision by the International Astronomy Society to deplanetize Pluto. So here you see Thanksgiving 2006. So November 2006 with Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto got demoted. No longer able to sit at the adult table, the adult planetary table. It has to actually sit at the kiddie table along with some others. And that's going to actually lead into 5C. And what is beyond Pluto? Nice starry background. Probably nothing true. That's all man-made, probably just to make it look like a starry background, which is what I typed into Google to get it. And all the objects we're going to talk about now are what are called Trans-Neptunian, or farther away than Neptune objects. This is a picture of the Sun and what's called the Heliopause, and this is the limit of the Sun's solar winds effect. And the first thing I want to remind you is that anytime we actually look at an astronomical diagram, we either get size or we get distance messed up, so that the scale is messed up, and this particular one actually does both. So if you look at the Sun and you look at the Earth, distance looks like 1 AU, which is fine, and then we actually go to 1.5 AUs for Mars, which looks okay. Jupiter's supposed to be at 5. Saturn is supposed to be at 10, and that is not 10 times as far away as the Earth. That would actually probably not even be on this screen. And the other thing, if the Sun is this big, the Earth can't be that big. So they've got the size as well as scale. It may look like 10 to the 1 and 10 to the 2 and 10 to the 3 and 4 and 5 and 6 are actually all the same size, but until you actually realize that 10 to the 1 is 10, 10 to the 2 is 100, that is not 10 times farther, and this isn't 10 times farther than that, and that's not 10 times farther. And we actually go all the way out to 10 million AUs, and that actually includes our closest neighboring star, but it's way the heck out there. And if I go into this picture, this is actually showing you that the interstellar space, which is here, Sun moving into interstellar space, the solar wind gets compressed on one side, expanded on the other. But this is the Heliopause, and this actually shows you 4 of the unmanned spacecraft we launched in the late 60s, early 70s. We have Pioneer 10, Pioneer 11, and then in the early 70s we had faster spacecraft. So we have Voyager 1 taking off after Pioneer 11, which is farther away because it's probably the fastest moving of all the objects in space, 75,000 miles an hour. Have Voyager 2 going off in this direction, and this is the projected path of Voyager 1. And if it keeps going out there, who knows, maybe even Alpha Centauri, if that is the direction. And I don't know what direction we're looking at for this Sun to put these out here to get Alpha Centauri. Alpha Centauri may actually be way the heck up there, but it's going to go in this direction and go for as long as it's either capable of going or until it hits something that makes it slow down and stop. So here are the TNOs, the Trans-Neptunian Objects, and you can actually see Pluto. If you remember, Pluto is a lot smaller than the Earth. It's even smaller than the Moon. We do have a few that are actually bigger than Pluto, which is maybe one of the reasons why Pluto got demoted, because we'd have to actually come up with a My Very Excellent Mother just served us 9 pizzas and come up with some other objects. But we have some of these objects where we can actually see orbiting bodies. I'm not sure what's going on here with 2003 LL61, but it looks like it's an egg, and it's got floating eggs, and you can see some of them are relatively small. They come in different colors, but they're probably all pretty much made of the same things. It's like comet material, basically planets of ices. Here is a picture of Eris, a dwarf planet. So is Pluto, and you can actually see it's moving in a stellar background. 3 pictures, and it's actually showing it to you because you can see it's moving in reference to that star, or at least that star-like object that could actually be a galaxy farther away. But you can see it's actually moving in reference to it, not so distant from these 3, but it looks like it's getting closer and closer to this star. There's Eris and Dystonium. I'm not going to butcher that name. Dystnomia. and this is an orbiting body around Eris. And again, this is probably a Hubble picture, but again, we're looking at an incredibly small object really far away, and resolution still is not real great. Here's another one, actually sitting right there. This is November 2003, and Sednia, I'm not sure. These are all based on somebody's idea of when these things were discovered in terms of astronomical or mythological objects, or sometimes even comic personalities. Then we're going to talk about clouds, and if you remember the Oort cloud from that activity we did with the virtual solar system, where we actually put the sun in the middle of, we hope, Forest Park, and we were actually getting this thing out in Nebraska somewhere where all the other orbits of the planets are relatively close. We have the Kuiper Belt. Kuiper Belt actually is sort of almost in the same frame as the orbits of the planets, but the Oort cloud is surrounded. You can see it's got one that's in the same orbit, but it's got lots of them around. And this one, we're maybe 30 to 100 AUs away, okay, outside of Pluto's Trans-Neptunian object. This one is more like 50,000 plus AUs away, really far out there. And I would like you to draw this. Doesn't have to be perfect, but I'd like you to get some idea of where the Kuiper Belt is. And then there is the orbital binary Kuiper Belt object. It looks like binary, so there are two of them. Not sure which one that is, but somebody actually found a particular pair of them orbiting the sun. You can see there's Pluto, so this orbit probably is 500 years to go around. Remember, it gets slower and slower as you go farther away. And then these guys, really far away, really slow orbits. And then the orbit of a comet. As a comet actually goes through space, it produces a couple of different tails in a coma, and these things actually put particulates out in space, and as the comet leaves, the particulates actually stay. And then as the Earth actually moves through these areas, this is where we get those shooting stars, or those astronomical events that actually allow us shooting stars to be found at different times in our orbit. And this particular orbit would give us one there and maybe one there. And then you have another comet that gives you some over here, and another comet over here, and another comet over there. And if it's on the plane, we can actually see this one once, twice, 3 times, 4 times, and we'll get a shooting star event. Here are the actual meteor showers, the shooting star events, and you have the quaternaries, which is coming out of a constellation, the Leonids, which are coming out of Leo, coming out of Aquarius, coming out of, that's Eta Aquarius, and this is Delta Aquarius, so we actually are coming out of two different parts of Aquarius. The Perseids coming out of Perseus, and then one coming out of Orion, one coming out of Leo again, and then one coming out of the Geminids. And you can see from January all the way through December, we get these moon phases. This is going to be 2016, so we've actually in this Geminids right now, and the peak is going to be the 13th to the 14th, and today actually is the 11th, so it's a couple days away. The problem is the moon's going to be full. It does give you an idea of how many meteors and little specks we actually see that seem to come out of a particular area, like you can see right there. If this was Leo, these would be called the Leonids. If it was going to be part of one of these Aquarius, it would be one of those, but you can see that they come zipping out of space. And these all happen pretty early in the morning, best view. And then you can see where it's going to be in terms of right ascension and declination. And you can also see what comet it's associated. So there is one with Halley, Swift-Tuttle, another one for Halley. So this actually may be Halley coming in, and this is Halley going out. And then you can see Tempel-Tuttle. These are two actually Tuttles, a person that actually got to see these asteroids and pick their location, along with Swift with Tuttle and Tempel with Tuttle. But you can see lots of information about meteor showers in 2016, and you can find probably 2017 up there soon. The orbit, and what you actually see is here is Draco, and the Bootes and the Big Dipper, and we have an area in space where these little particulates of comet and or asteroids come in, and that's called the radiant. And this is what actually gives the shower its name. Is what point in the sky do these things tend to originate. Okay, there is a comet. The nucleus of the comet actually is going to be relatively small, but as it gets close to the sun, the gases in this comet vaporize, and then they get swept away. Some of them with solar wind, and some of them actually for the motion of the comet. And then we also actually notice as it comes through and starts to sublimate, that actually means that the ice is turning into vapor rather than turning into a liquid, and then it gets larger and larger, and then as it moves, and you can see this particular, what tail are we actually showing here? Doesn't say, but I think this is the gas tail. I think this is the ion tail. No, I'm sorry, that's the dust tail. This is the plasma tail to the ion tail. So the ion tail gets pushed away from solar wind directly opposite the sun, and then the gas tail actually shows a little bit of motion. Normally you would think these tails are actually moving away from its orbit, but it's really being forced away from solar wind, so it's actually being pushed away. So the tail is always pointing away from the sun, and that's not good. I'm going to stop this. I'm going to actually say that this gets animated and it appears, and I'm going to save, and I'm going to go back in because I just put that in, and you can see that I actually want you to draw 3 pictures. I would like you to draw this one. There's the nucleus of the comet. There's a coma. Nucleus may be a couple kilometers across. Coma could be 100,000. And these could be millions of kilometers long, but we actually get what's called a dust tail, and we get a gas tail. There's the coma. This is a better picture than this one, but it still is being drawn. The nucleus is in there. We get the coma, and then we get a dust tail, and we get an ion tail. And then this is the one I'd like you to draw. So there's the sun, and we get the gas tail actually moving directly opposite the sun, and then we get the dust tail moving a little bit from the motion of the sun and also the motion of the comet, and we actually get this. And then if I click this, which I'll go ahead and click, it is a shock wave, so it will not open on devices. And if we take a look at it, I'm just going to close this because that's instructions. If you did that, you may want to go through it, but basically it just shows you how to do slow down, speed up. And if you take a look at this blue one, that is the orbit of a comet, and Borrelli, and I'm going to zoom out so I can see the comet. There it is right there, and you can see the speed changes, and there's the tail that moves opposite the sun, slows down. Again, farther you are away, the slower you can move because of gravitational pull. And then it speeds up, and here comes the tail again, tail moving away, the dust tail and the ion tail actually showing a little bit about motion. And then here's the other picture, which is showing you the sublimate. As it sublimes, it actually produces the cloud, and the cloud gets pushed away by solar wind, as well as something about the motion, and then we actually get the dust tail doing this one, and the ion tail being pushed away. And then the last slide, this is actually Stardust, and Stardust went through the tail of a comet and actually into the coma of the comet and got a picture of the nucleus. And we actually found that the nucleus probably has much more detail and much more things going on than we ever knew. And I'm sure we'll learn more about it later on. Okay, that's the end of 5C. Thank you much.